Hi everyone, thank you so much for joining us today. We have with us Muhammad Gohar Javed. Gohar is currently pursuing his master's degree in electrical engineering and computer engineering at University of Alberta under the guidance of Dr. Li Cheng and Dr. Xingyu Li. His research focuses on applying generative AI and reinforcement learning for 3D human motion control. Today he will be talking about his latest research paper, which was published in CVPR 2024, titled as MoMask, Generative Mask Modeling of 3D Human Motion. Thank you so much for your time and overview.
Okay. Um, yeah. So I would be talking about this recent work that is published in CPR 2024. It's called MoMask. We name it. It's generative mask modeling of 3D human motions. I know the title sounds a bit obscure, uh, but we're trying to use generative AI techniques to model or synthesize 3D human motions that can be used in any kind of virtual environment to control digital humans. So yeah, this work was in a collaboration effort with me and then a couple of my lab mates. And then here I have a QR code that would take you to the website of the project if you want to learn more about it, or if you want to see the code, the paper, everything is available from the website. And this QR code will appear later in the presentation as well. So if you miss it right now, it's okay. Right. So I'll just go over what the agenda would be for today's talk. So I start with the motivation of why we want to work on this problem. What is the goal, and why do we design our method in a certain way? And then I'll talk about the key features of what improvements or what contributions we make in our work. And then methodology, explaining what we actually do, some experiments and results, and then a very short conclusion. And then we'll take some questions as well at the end. Yeah. So let's get started with the motivation. So our goal is to enable digital character control in animations, in games, virtual reality, so any kind of digital environment that you can think of where you might need to animate characters, human-like characters. Our goal is to enable control for those characters using just natural language. So we propose a novel generative AI method to synthesize and edit realistic and diverse 3D human motion using just natural language. Yeah, so the semantic of what the goal is, you just take a natural language description, which in this case is walk forward, take a spin on your right foot and walk back. You need an AI system and which does this for you. Right. So yeah, just natural language, you give it to a model and you get what you're describing in your text prompt at the output of the model. And similarly, you can say something like a person kicks and jabs several times, goes into the model, and you'll get a motion like this. Now, there are like a couple of challenges. The motion needs to be realistic, how actual humans would move. It shouldn't be like robotic. And then it needs to be diverse because natural language is very semantic. It does not explain, it does not describe in depth what you want from a system. So one word can mean several things, or one text prompt can mean several things, and it can be interpreted by differently by different people. And then also, every person does not walk in the same way. Every person does not run in the same way. So we need that like human diversity in the system too. Right. So that's why we're using a generative AI technique, because we want diversity. We want it to learn from the data distribution. I am sure that everybody here must know what generative AI is, how it works like, but I'm just going to go through a little bit of a background to, if in case anybody needs a little bit of a refresher. So yeah, generative AI learns conditional probability distribution of the data and then samples from that distribution. We have a bunch of different techniques, GANs, VAEs, diffusion models, but all they're trying to do is using some kind of surrogate objective to learn the probability distribution of the data. It can be conditional, it can be unconditional, and then there's a sample from that distribution. So yeah, for example, we have a generative AI model, and if we give it a conditional signal, which can be present and cannot be, it gives us a synthetic data, uh, and then we measure its distance with the real data, and then we have to minimize this distance to our objective, and that's how we update the model. And in our case, our conditional signal is text. Our synthesized data is motion, and then real motion. So we're trying to limit the distance between the probability distributions of our synthetic motion and the real motion that's collected from actual human beings. Right. So we have a lot of different generative AI techniques. We have GANs, we have variational autoencoders, we have diffusion models, autoregressive transformers, or autoregressive transformers are basically large language models, GPTs, BERTs. There's a lot of different large language models. They're all autoregressive transformers. And they all have their pros and cons. For GANs, we get really high sample quality and fast sampling, but they're not good at mode coverage or diversity. They do not learn the entire probability distribution well. And then in VAEs, we have very fast sampling and we have very good mode coverage or diversity, but we don't have high enough quality samples. And then with diffusion models and autoregressive, we again have high quality samples and good mode coverage, but it's not fast because both of these models take multiple steps of inference to generate one sample. So yeah, so there's pros and cons in this work. We've tried to do something where we build a model that has that encompasses all these three aspects. So we want fast sampling, we want high quality samples, and we want coverage. So yeah, I'll go into more detail of how we try to do that. But yeah, we've tried to cover all these three aspects. Yeah, so a little bit about previous works on generating human motion. There's been a lot of interest in this field. And we have this paper from CVPR 2024, which uses a VAE or variational autoencoder. And then a couple of them use diffusion models from 2023 again. There's also some works with autoregressive transformers, discrete diffusion models, and then retrieval augmented diffusion model. And then our work, which is this year's CVPR, uses a new kind of technique that hasn't been used before in this field, which is bidirectional mass transformer. I'll explain it in more detail, but just to give a preamble, it's something like BERT. If you've heard about the BERT language model from Google, it's similar to that. Right. So, what limitations did we observe in the past works? First of all, like VAE methods have very low fidelity, as I mentioned before as well. They have fast sampling and they have high diversity, but their quality is not good. And then diffusion and autoregressive methods are really good at diversity and high quality samples, but they have a very time-consuming inference process because they take thousands of steps to generate one sequence or one sample. And then autoregressive transformers and discrete diffusion models, which need some kind of tokenization technique. But that tokenization technique is always error prone. And they mostly just use a simple autoencoder, which is a lossy process by default. So yeah, that introduces errors in autoregressive transformers and discrete diffusion models. And then autoregressive transformers also have another limitation where they use just one directional modeling, because they would just look at the past tokens and predict the next one. They won't look at the entire sequence like diffusion models or VAEs. So they have limited expressivity. So we have a lot of these limitations. Some of them have low fidelity. If they get high fidelity or high quality, they're time consuming. So yeah, we've tried to, in our work, we've tried to take care of all of this in one way or other. Of course, it's not perfect, but it's an effort towards what we want. So yeah, Now, we've talked about the motivation. Now I'll go into a little bit of key features of our method. Uh, and I'll mostly address how we're trying to overcome the limitations that I've mentioned just now. Right. So overview, it's just a brief semantic of how our method works. So we get motion tokens. I'll get into detail how we get motion tokens because it's not actual motion. Uh, Tokens, you can think of it as in terms of LLMs, because in LLMs, every let's say word is a token, and then that's how you represent the word as some kind of an embedding, and that's what like in these kinds of generative transformers lingo, we call this a token. So for language, for example, every word would be a token. In terms of motion, every pose. So if you think of motion as a sequence of poses in time, so every time step would be one token. Yeah. So we get the motion tokens, we mask them. So we just randomly mask some of these, which are shown in like gray here. So we still can see the green tokens. We cannot see the gray tokens anymore. We pass this masked token sequence into the bidirectional transformer encoder. I'll again go into more detail, but bidirectional means it looks at every token attends to every other token, and then it predicts the masked tokens. And then, of course, it's conditioned on text, which comes from a text encoder. Yeah, so a brief overview is that it's a masked modeling technique uh, rather than autoregressive modeling, which just looks at the past. It masks some of the tokens and looks at all the tokens while predicting the masked ones. It does not predict only the next token while looking at the previous tokens. And it's bidirectional again. Every token attends to every other token. And it's very simple, just an encoder, only self-attention layers, nothing too complicated. Right, so the key features here are expressivity. First of all, we use a multi-level residual quantization or tokenization technique, which I'll go into more detail about. And it significantly enhances the representation capacity of our tokenization, which enables generation of high quality motions. And then it's robust and efficient because we use a bidirectional mass modeling technique. It ensures robust generation by minimizing accumulation. Because if you're just using past signals, you can think of a case when you get a false prediction, and then you're predicting the next one based on that false prediction, and that error just accumulates. But yeah, when we're doing bidirectional mass modeling, we predict them, we forget some of them, and then we predict them again, so that which minimizes our error accumulation. And then it also offers substantial efficiency gain because now we're not doing token by token, we're predicting all of them at once. And then, of course, because we are masking it, so it allows editing capability by default. For example, you have a motion sequence, you want to change the middle portion of the motion sequence, you can just mask it and predict it. So you don't need any extra task-specific fine-tuning for this. You can just use this model as is out of the box for editing capability as well. Right. So that being said, I'll dive into the methodology now, how we design our models. So it's a three-stage modeling approach. Our first stage is motion tokenization. As I mentioned before, tokenization, you can think of it in terms of LLMs. Each token, like in LLMs, where every token is a word, we also need to tokenize motion in that case so that we can use transformers to model it. So first of all, we think about how we should tokenize motion. So for this, we use a residual vector quantized variational autoencoder. It's an autoencoder which is variational, which means that it has some kind of a diversity or some kind of stochasticity induced into it. And then it's vector quantized, which means that it's just discretized. I'll go into more detail again, but just to give a summary of what the technique is. Right. So we get the motion, which looks like something like this. It's just a person walking in a circle. the motion sequence again is represented as a sequence of poses. Those poses are passed into an encoder, which is a very simple 1D convolutional encoder, and then we get the output. The output then goes into a quantizer. What a quantizer does is that it just quantizes the representations into discrete tokens, so that we, at the end of the day, we learn a code book or like a dictionary of, let's say, 512 tokens. And then that's all we have to represent our motion. And then different combinations of those 512 tokens would represent different motion sequences. Right, so what's happening here is you get the representations from the encoder, you quantize it, and you get quantized representations here. Now the problem here is because there has to be some kind of a gap between what you get from the encoder and what your codebook has learned. There's always going to be some error there. And then if we just use this, which most previous works do, they just use this representation, it is a lossy process. So to minimize this loss, this kind of like compression loss, you can think of it as, we take this representation that comes from the encoder and we take a quantized representation. Now there has to be some kind of difference between that. So we take that difference, which we call a residual, and then we quantize that residual again. Right. So any error that comes from here is quantized again. And then any error that comes from this quantization is quantized again. So we do it like V number of times. In our paper, it's 6. So we have these 6 quantization levels. We quantize it, take the difference, quantize again, take the difference, quantize again. So now in this case, every motion is represented in 6 sequences, 6 quantized sequences. And then in the decoder, we add all of them together to get one final quantized representation. And then that after the decoder, we get the output again. Now, as I mentioned before, these come from a code book which is pre-learned. So that code book is a learned dictionary of, let's say, 512 vectors. So now what we can do is that we can just use indices from the code book. So instead of having these vectors, we can have, okay, we can say that this is the first vector, this is the second vector from the dictionary, this is the 256th vector, this is the 15th vector, something like that. So now we have just indices, integer indices, which we call motion tokens, which refer to specific vectors from the dictionary that we can then use to decode them. Right, so now here we have just indexed them. Now our base, and we have a series of motion tokens. We first of all have our base motion tokens, and then we have residual motion tokens depending on how many levels we use. In our work, we use 6. You can use more as well. Right, so each of these token sequences is just a series of integers, which refer to indices of the dictionary that we've learned. Right. So yeah, this is how we tokenize motion, and then we use this tokenized representation of a motion in our transformers to learn their distribution, and then we can sample from them. Right. So moving forward, now I'll talk about like our base token mask modeling. So as you saw before, we have base tokens and then we have residual tokens. So we have to like model all of these different levels, so that when we are trying to generate motion, we generate all of these tokens and then we pass them through the decoder to get our motion. Right. So for the base tokens, these ones, we have first of all a masked modeling technique, which is the main generative part of our approach. And it consists of a bidirectional masked transformer encoder. Right. So we get the motion tokens. T just represent tokens, and 0 means that it's the base layer tokens. And then we get those, we mask them, as I mentioned before as well. The masked tokens are concatenated with the text encoding from clip, which is the text encoder we use. And then we pass it to a masked transformer, which again is a bidirectional transformer encoder. And then we get the predicted tokens, which are represented as T hat 0, because this is still the base layer of the residual. So this is the main generative part of our model. The VQVAE just gives us representations in a latent space, which is also quantized, and then that quantized representations we model using a mass transformer using this mass modeling technique. Yeah, again, the transformer consists of L number of layers. In our work, we use 8. Each layer has just a self-attention and a feed-forward network. So very simple, just it's a simple transformer encoder that's pretty much the same as what you saw in the attention is all you need paper. Yeah, so this is the base token modeling. It's just masked tokens. This transformer here learns to predict the masked tokens based on all the tokens that it can see, and also the text. Right, so now we have the base tokens predicted. Now we have to predict the residual tokens. So for that, again, we use a bidirectional transformer encoder. We get the motion tokens, right? So here, this can be the first layer, because let's say we have 6 levels in our residual quantization. So to model so the first layer we get from the base tokens. The second layer, we would use only the first layer tokens. For the third layer, we use the first and second layer tokens, and so on. So for like jth layer, it uses 0 to j minus first layer tokens. So we concatenate all of them together on the channel dimension, and then we concatenate the text encoding, and then we also concatenate an ID token, which tells our model that which level of quantization you're looking at. So if the model, and then we use this one model to model all the quantization levels, all the token levels we have. Yes, this ID then tells the model it's the value of this ID is between 0 to j minus 1. So it tells the transformer that you're only looking at, for example, the first layer tokens, or you're looking at the first and second, the first, second, and third, and so on. And then, yeah, we pass it the tokens from all the previous levels, and we get the prediction tokens of the next level from this transformer. Right, so it's 3 models that we've talked about so far: the VQVAE, which is the tokenizer, then the mass modeling mass transformer, which models the base layer, and then this residual transformer, which models all the other layers, depending on the base layers. And then again, this is also just a very simple transformer encoder with self-attention and feed-forward network. Right, so yeah, so we've talked about like 3 different stages in our pipeline. This is just like an overview so that you can look at everything in one screen. So we have, first of all, we have a motion residual VQVAE, which gives us a latent representation, again, a quantized latent representation, which consists of different levels of tokenization based on the residuals from the previous layer. From here, we get V different levels of tokens, which is again 6 in our case. And then the first layer, the first level, is modeled by a mass transformer, which learns to predict masked tokens based on the other tokens that it sees. And then once we have the base tokens, we use the base tokens and the subsequent level tokens to predict the next level token. So this transformer just looks at tokens from all the previous layers that predicts the next layer tokens. So this is not a masked modeling technique, and this is deterministic. There is no stochasticity involved here. The only stochasticity we have is in the match modeling, which is our main generative part of our model. Right. So that being said, I'll talk a little bit about how inference happens, because now you can see here that we have how we train it is that we randomly mask tokens from an input sequence and then predict those tokens. But how would we do that in inference, right? How would we change the input outputs in inference so that we can generate new motion, which the model has never seen before? So how it works is that we start with all the tokens being masked. So this is our masked transformer, which predicts masked tokens. from the base layer. So we start by all the tokens being maxed. We concatenate the text embedding with these match tokens, and then we pass that into the match transformer. The match transformer gives us predictions of all these tokens in one pass. That's what I also meant when I said that we don't autoregressively, it's not an autoregressive transformer. It does not look at just the previous tokens and predict the next one. It predicts all of them at once. So it gives us a prediction for all the tokens it sees based on now, because it's only seeing the text. So it's just based on text. And then we remask it. We remask the predictions, and then we only keep the top 5%. So we have a score, and then we only keep top 5% of the tokens that it has given us, and then we'll mask the others again. Now, when I say top 5%, that's tunable. You can change it. It depends on how many steps you're using to make the final prediction. In our work, it's very few. It's just 10 steps, which is a lot less than autoregressive or diffusion models, because diffusion models use closer to like 1,000 steps or minimum 50 steps, even if you're using DDIM sampling. And then autoregressive based is dependent on the number of tokens you have. So let's say you have 50 tokens, you will still have to make 50 predictions. But in this case, since we predict all of them at once, and then we keep a good portion of them, we only need, in our work, we only need 10 steps to get a very good motion at the end. Right, so we predict all the tokens, we remask it, we repeat this for a certain number of steps, which is 10 in our case. And then at the end of the day, at the end of those 10 steps, we have all the tokens. We predicted all the base tokens now. So this is like, this step is what generates the base layer. This is where our generation, quote unquote, comes in. This is the stochastic part. Now that we have the base tokens, we pass that into our residual transformer here. And then the residual transformer predicts the next level token. And then both the next level tokens and all the previous level tokens are passed into the residual transformer again. This is repeated V number of times, because if we have V different levels in our quantization, that's how many times that we have to repeat this process for the residual transformer, and then we'll get all the residual levels of the tokens. And then to decode them, we just add them together in this step, and then we pass it into the decoder, and then we'll get the final version. So all in all, counting the 10 steps we have for the match transformers, 6 steps in our case for the residual transformer, and then when passed to the decoder, I can say, I mean, it's not 6 because you already have 1, so you just have to predict the remaining 5. So 10, 5, and 1. So we have like 16 steps, which is around less than diffusion models or autoregressive models. It's not still perfect, of course. In a perfect world, we would just have 1 step, and we would get what we want. But yeah, this is at least some effort towards that direction. Right. So now we have these 15 forward passes from different networks, and we get our final motion. And that's how inference works. Right. So having been talked about methodology, I'll go into a little bit more details of the experiments that we did and the results that we have. So you'll see some more cool stuff now. Some of the results. I'll just go over the quantitative results first, and then I'll show you some of the functions that we've generated. Right. So this is from the paper itself, this table. We compare with a lot of different baselines. A lot of past works have been done on this task. And there's 2 data sets that we've experimented with. There's Human ML 3D and KIT ML, or Clarity ML. Both of them are text to motion data sets. Every sample has a text and a motion. And then we have 4 different metrics that we use to measure our performance. I wouldn't go into the mathematical details of these, but roughly our precision and multimodal distance, these 2 metrics measure the text to motion alignment. So it measures how loyal is your generated motion to the input text that was given to it. So it measures the semantic difference between your text and your motion. And then FID measures your fidelity or quality, like how realistic your motion is, how high quality your samples are. If there's any, motion should be realistic. There should be no jittering. There should be no sliding. So yeah, it measures all of that. And then multimodality, this metric measures diversity. So yeah, you can see that we do very good on a lot of these metrics. We have state-of-the-art performance in our precision in the FID and multimodal distance. For human-human ML 3D, we lack a little bit of multimodality or like diversity, but that comes with like a trade-off because we wanted our motion to be more loyal to the text that it gets. And then again, in KitML, we do very well on most of the metrics. Yeah, it's by no means a perfect model. There still can be a lot of improvements. And then we also did a human perception evaluation where we took a certain number of motions generated from our work and from previous works. And then we also did our work versus ground truth, which is actual data from humans, to see that and then we asked users to vote on which one do they like better, or which one looks more realistic or more human-like to them. And then in our results, we found out that our results were preferred over other methods most of the times. So like over 50% means that our method was preferred like 64% of times, like more than the other one. The other one was, in this case, preferred like 36%, and then so on. So we have like over 50% in with between models, and then if we compare it with ground truth, we still have 42%. So in fact, 42% of the times, people thought that our model's generated motion was better than the actual ground truth motion. So yeah, I mean, which goes to show you that it can produce very realistic motion that looks really good to human perception, because human perception is, in fact, at the end, the goal of every generative AI technique. And then we also want to see efficiency, because as I have rambled on about, we are faster than diffusion and not regressive so many times. But yeah, we also have some proof. So this graph shows you FID, which is the sample quality versus average inference time. So we sit right here at the bottom left corner of the graph, which means that our FID is very low and our time is also very low. And then you can see like all the other methods, whether they are like, for example, diffusion-based methods that take like 10 seconds. This is also diffusion-based methods, takes a lot more time. This is a diffusion-based method, but it uses DDIM and it uses a latent representation. So it got the time down to like 0.22 seconds, which is still double ours, but its performance is not that good. FID. So yeah, that was all for like quantitative results that I wanted to show you. I'll go through like a gallery of the motions that we've tried and we've been able to generate. So like something like this, you just take a text, you give it to our motion, and you can get your generation. So in this case, it's just running on a treadmill. So you see a person or a character running at a spot just continuously. And then something like this, which is very, very, very detailed, so much more detailed than your like average description. So it tells you when a person stands, crosses left leg in front of the right, lowering themselves until they are sitting, both hands on the floor before standing and crossing legs. So you can imagine a situation where there's like an animator that's building a game or some kind of animation, and they want very fine-grained control on what they want their character to do. So yeah, we wanted to test that, and then it even gets the legs right, because you can see that the left leg is in front of the right one. and then both hands on floor. So it gets very, 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 fine-grained details for the text. Not in all cases, but in most cases that we uh, tested, it does pretty well. And then again, a man is walking forward and then steps over an object and then continues walking. So we see these kind of motions when there's like the actor is doing something and then you want to do something else, or like have like a break in between their like regular motion sequence. So yeah, it does considerably good on these things as well. And as you can see, like the motion is pretty realistic. It's not overly robotic, and that's like also thanks to the work that has been done on taking pose sequences and building characters out of it. Uh, and then yeah, this prompt says a person takes 4 steps backwards, and yeah, I mean you can count them. It's like 1, 2, 3, 4. So yeah, it takes a lot of semantic and details from the text and a lot of fine-grained geometric details of the text too. Um, yeah, and then again, since it's a generated model, we need it to be diverse. And then we want that if we give it one text sample, it gives a different styles of motions. So for example, if you're playing a game like GTA or something, and if anybody's played it before, you would have seen that if you take out a gun, everybody starts running away, but they're all running in the same way, which is like not realistic. So we want our motion to be diverse. We want it to be human-like because humans do not move always in the same way. So like in this case, for example, we say jump, pump, and then land. So we see a lot of these different kinds of jumping variations where this one even does a spin. And then, yeah. And then again, this one says a person was pushed but did not fall. So yeah, because it does not explain how the push happens. So there's a lot of room for creativity here. And our model seems to push backwards, push sideways, stronger push, weaker push. So it generates motion that like contains that diversity that's inherent in any kind of language prompt. And then again, as I said before, because it's a mass modeling technique, you can just mask parts of your motion and generate them again. So it supports editing out of the box. You don't need any task-specific fine-tuning for that. So yeah, I have a few examples of editing. This is in-betweening, which means that you have a motion sequence. You take out a chunk from in between the motion, and then you generate it based on some text. So in both of these samples, purple is the input. So purple is the motion that was generated, like the main motion. And then when it changes to this other color, cyan, then it would do what is described in the text here. So we want the transition to be smooth from like the original motion to the edited motion, and then we want it to do what it's doing, what we've said in this text. Right. So you see a character here just doing like some kind of a warm-up thing, and then it falls down and gets back up quickly, and then continues doing that. So look at it again, purple, cyan, which is the generated, and then it continues doing the same thing again. So yeah, and then in this case, the person is walking, it gets pushed as soon as it's cyan, and then it starts walking again. So we see like smooth transitions between the edited and the input motion. And then it obeys what we tell it to do in that text prompt for the edited portion. So yeah, so these two were examples of in-betweening when you change something from between the motion. And then we also have suffixing, which is you just change at the end. For example, in this case, we have a person bows. So a person is doing grips, just like random stuff. And then, I labeled it, I think, wrong. So this one is squats. So a person does a squat. And then this one is bows. So a person is walking forward. And then at the end, you want it to bow. And then you just add this, and then it bows. I'm sorry for this confusion. These are flipped. And then prefixing is something that should happen before our input motion. So here we have a person who gets up from the ground, which it's doing right now, and then it goes on to dance or whatever it's doing. And then a person is doing the warm up. I'm guessing that it would be running after this, or yeah, or like just walking. So yeah, you can edit it, you can prefix new motion, you can suffix, you can in between. Depends on like it's because you can mask from any portion because it's bidirectional. It looks at all the tokens to predict the mask tokens. You can mask from anywhere and do that. But yeah, of course, as I said, it's not perfect. There are some failure cases. In this case, for example, we say a person is crouching, then stands, and then crouches again. It does not really follow that. Our hypothesis is that crouching is a term that it didn't see in the in the ground truth set. But since we're using clip, we also expect it to be good at generalization for language terms that it has not seen in the training set. Because clip is a much larger model that has been trained on much larger data set. Uh, but in this case, I think like crouching might not be even a common term for like something like clip. Because crouching is more action focused than images because clip is just trained on images and their captions. But yeah, it could be for other reasons. And then here we see a person does a spinning dance move. So whenever we see rapid movements in a person's root position, that's where it kind of like sometimes fails because you can see this motion is not, it's very finicky, it's not realistic. It's just sliding over the floor and it does not know what to do here. Um, so yeah, again, monologue, there still is room for improvement. And then yeah, so just a very brief conclusion. What works well? Again, we can produce high quality or high fidelity and reasonable diversity samples. It understands most language prompts. It struggles with words like crouching, which are a little bit unorthodox. And then it supports editing by default. It has high efficiency. And then what does not work is that, again, complex prompts with multiple steps sometimes do not work in the case of, for example, the crouching example. And then long motion sequences, we also notice that because when the motion is up to like 10-15 seconds, it works very well. But if you go beyond that, like a minute long sequence, it does not work very well. It would just do like a repeated motion movement again and again. So that's a good future direction to explore how to generate longer sequences of motion. And then rapid movements, just like in the spinning example, when there's like rapid movements in the root joint, it just does not do very well in that. So yeah, this is like a brief summary, what works well, what does not, and what can be potential future directions. So yeah, I think with that, I'll leave around 10-12 minutes at the end for any questions that you have. Thank you so much for everybody who came. Again, if you want to learn more about the project, you can just scan this QR code right here. It will take you to the project website. And then if you want to contact me about anything, if you want to talk about the project or anything else, you have my email address, and then this QR code will take you to my web page at the lab. And then from there, you can get my LinkedIn and email address again. So yeah, feel free to reach out if you have any questions or if you just want to talk about research or whatever. I'll be happy to. And yeah, again, thank you so much for coming here.
Great session. It was really knowledgeable talk. I had a few questions. So, since you are using Clip for text encoding, and from what I have seen and tested with few vision language models and even Clip itself, that it does not understand spatial relationships very well. For example, if you want to classify between which is left and which part is right, or if there is some cropping or some kind of augmentation in it. So it does not understand that thing really well. But I thought that in your case, your model understands spatial relationships really well, that it is first standing or it is crossing the left legs first and right legs first. So do you think it is because of the data set quality or because of some other architectural change that it understands these spatial relationships really well?
Right. I think one problem is you mentioned that it does not do well in when you're using vision like images. I think the reason is because in our data representation in motion, the left and right are very well defined, because there would be one joint position for the left arm and another joint position for the right arm, and then uh, in our data set too, we would have a lot more mentions of left and right, more so than like image data sets, because in image you do not talk about left or right. But like almost every other motion sample in our data set would have a mention of left, right. So yeah, I think that that is a reason. So first of all, in our data, left and right are very well defined, which is not in the case of motion. In the motion, because which is not, sorry, which is not in the case of images. But then and then also our data set sees a lot of lefts, rights in our samples. And then we also tried like other like more advanced text encoders other than clip. Um, they provided like a little bit of an improvement, but we didn't see any. It was not worth it to use those because they would increase your kind of like throughput of the model. Sorry, latency of the model. So yeah, we tried like T5 based models, we tried LLMs, but we at the end we found out that clip, and this we only use the base level, the base model of clip, and that works pretty well in our case.
Right. Makes sense. And do, do you have some other insights on whether it will generalize on other kind of motions which are like not very explicitly defined in like to show a few examples in which in that case it was not working well. But do you have some cases where it is not where the motion is not very well present in training data set, but it works well because of sleep or because of the testing level?
Um, yeah, we saw that, for example, let me think about it. There were a few cases, like in our data set, we don't have a lot of like martial arts, or we don't have like sword fighting. Um, I, I I should have included some of those samples here, but like we experimented. Like for example, we gave it a text prompt of a person is attacking while sword fighting. So you can imagine that if you have a sword and you are in attack or like in fencing, so it still did a pretty good job, even though we didn't have any samples from sword fighting in our data set. And then some of the fighting sequences, it seems to know the difference between like boxing and kickboxing and wrestling. Um, so yeah, I mean, we saw some of those samples. Again, there were still samples that did not work very well, but like there were still some cases that were not present in the data set, but the model still worked well on those.
All right. And did you use any kind of like physics equation or something like that to make sure that the movements are same as human movement or follow the physics of human, like they're not robotic movement? Or did it all happen with the help of simple training?
That's a very good question. A lot of people do that. A lot of works try to use some kind of a physics engine or use some kind of physics equations to guide the model to generate more physically plausible motion. But we didn't do that. This is our model is just data driven, because we wanted something that would scale with the more data that you have, and we've seen this trend in like a lot of other cases of AI when people try to induce their like self knowledge, their priors, things like physics and others into their modeling techniques. But at the end, what we saw that the thing that works best is something that can just scale with the amount of data that you have. So yeah, we did not use any kind of physics equations or physics engine. Everything in our motion is learned from just how the data is. That being said, again, because we don't have a lot of data right now, it's not entirely, uh, it does not obey all the physics. So there's still room for improvement here. And then, yeah, there's like a lot of physics techniques that you can still use, like on top of this model. You get the output, and then you can do like some kind of a post processing on this to improve those things. But yeah, like in our work, we didn't use any physics at all.
Oh, sounds good. And one last question that I had was that in the latest diffusion models, there are like schedulers and stuff which kind of reduces number of steps very much, like maybe less than 5 steps, I guess. So I don't remember exactly, but they are like pretty much real time or can run on mobile devices even. So do you think that if we use such a model that would improve the results of these in this case?
Yeah, I mean, we've been thinking about exploring that direction too. There has been like traditionally diffusion models have taken like the original DDPM, and when you don't use any kind of implicit modeling, you have a lot of steps. And then the VIM came, and then you could do that the same thing with just like 50 steps. But now, yeah, there are more and more techniques or more diffusion-based models that use very less number of steps. But yeah, we haven't explored that yet. And I guess if they work for image, one thing that I've noticed is that they do still need a lot of data to train those kind of field models. So they might not work in the same way for motion because we have a limitation in the data because we only use motion capture data from real humans, and you cannot find that at scale on the internet as you can do with images. So yeah, there's still like a bit of a domain gap there. But yeah, it would be really interesting to see how well they work and how we can use the Fusion to like even make it better.
Okay, thank you. If you don't have any other question, we can end the session here. Thank you so much, Gohar, for your time. It was really an insightful session.
Yeah, no, of course. Thank you so much for inviting me, and thank you so much for your questions.
Yeah. Take care, everyone. Bye.
Right, take care, everyone. Bye bye.